Okay, so now let's look at solar cells, properly called photovoltaics. So let's review our ideal JV curves for a diode, semiconductor diode. So in the dark, we have J equals J naught times x to the QV over KBT minus 1. And now to this, we can add the non-ideal current, J naught, and we're going to use the example of recombination inside the depletion width here. So the so-called neta equals 2 recombination inside the depletion width, QV over 2 KBT minus 1. And I'll get around to why this is in a little while, why we need both parts. So the current in this case is lower, so the JV curve becomes softer in the forward direction, but it actually becomes larger in the reverse bias direction. Meaning that there's more leakage current in the reverse bias direction. Now when we shine light on a p-n junction diode, we'll displace whichever one of these curves is dominant in this particular diode downwards, and we'll actually be able to extract work or electrical power from the device. Now, what's important to remember is that we're imagining this device hooked up to a resistive load here with a load line of slope 1 over our load, such that the intersection of these 2 points define the intersection of the JV curve and this load line define a unique operating point given by V and J of operation. So this load can be varied from infinite, meaning that we'll have zero current and voltage applied, all the way to 0, where we would have a short circuit. And these 2 points are given special names. So this is the open circuit voltage, and this is the short circuit current. So in the ideal case, JSC is simply equal to J light, and that's very closely true for most reasonable devices. So the actual maximum power that we can extract out of this solar cell becomes a good question. And it turns out that the power, remember, is given by, so the power is a function of voltage, is given by the current I times by the voltage. So we can write it in terms of power per area as J of V times V itself. And this function, once you look at the JV curve, looks something, this should go up rather linearly and then have a peak and come back down. It should look something like this, where this is the VOC. The maximum power point is very close to VOC because of the sharpness of the ideal JV curve. And JSC would be here because you have no voltage and thus no power. So this maximum power point tells you where you should operate your solar cell in order to extract the most power. We can sort of graphically represent it on the original JV curve for an ideal, for a very ideal solar cell by defining VOC, JSC, and this imaginary maximum power we could ever extract, given the JSC and VOC, would be given by this rectangle, or the power rectangle of JSC times VOC. So we can define the power efficiency as some three factors multiplied together. So we define a fill factor times VOC times JSC, and then we divide it by the power coming in from the sun or whatever other light source is operating. So this fill factor then is given by the rectangle defined by that maximum operating point that we just defined here. So it's essentially a measure of how square the IV curve is. And obviously if you have an exponential function like this, it's never truly square, and the highest fill factors are in the high 70 to low 80% range. So for the most ideal diodes ever possible, you can define a limit there that's something around 80%. So this is the actual power that we'll get out compared to the maximum theoretical power rectangle if we had some non-existent device that could actually operate at both VOC and JSC simultaneously. So the power efficiency is defined like so. And now we have to talk a little bit about the spectra coming from the sun and qualitatively argue why the band gap matters in this problem. So let's look quickly at our semiconductor and figure out what determines our VOC first. So if we have a semiconductor with band gap Eg, it can absorb a portion of the solar spectrum, which we can plot now as an imaginary black body spectrum. The real one has some more details due to atmospheric absorption, but basically if we go between about 200 or 300 nanometers out to something like 3.5 to 4 microns, we capture almost all the power coming to us from the sun. On Earth, we call this the air mass 1.5 spectrum, and that would refer to the real one that looks like the black body curve, but with some very sharp dips due to atmospheric absorption. Now, if I have a particular semiconductor that I'm going to make my solar cell out of, let's say silicon, its band gap will mean that it can only absorb photons that are to the left or at shorter wavelengths. So the total photon flux is going to be the photon flux is a function of wavelength times a step function for the semiconductor's band gap, and then we're going to integrate d lambda and get a total current that can be generated. So again, only photons with energy larger than the band gap can be absorbed. So therefore, we can quickly see that as the band gap is reduced, as the band gap gets smaller and smaller, you can get more and more current. Now, however, where does the voltage come from? So now we have to talk about generation rate and density of states. So the effective density of states, NC and NV, for semiconductors are of order 10 to the 19 per cubic centimeter. Oops. Now it turns out in the entire solar spectrum, there's approximately 10 to the 20th or so photons per second per meter squared. So and it's spread across a large region of energy. So that means that it's very hard to achieve high injection conditions in any semiconductor under sunlight or radiation. Now, let's remember our definition of the quasi-Fermi levels. So we can say that EC minus EFN is going to be proportional to kBt logarithm of n over nc. And this n here is n naught plus delta n, and this delta n in turn is our g times tau in the lifetime approximation. So what this tells us is the larger our minority carrier lifetime and the larger the illumination, the larger our delta n in steady state will be, and thus the closer the quasi-Fermi level will be to the band gap, or sorry, to the band edge. Now, in general, though, you can see from this logarithm function that it's very hard to push the quasi-Fermi level actually up to and coincident with the band edge. So a decent rule of thumb is that for most semiconductors, you're going to lose about 0.4 volts under sort of good semiconductors with reasonable lifetime in the few nanosecond range, and carrier injections set by a band gap that's something between 1.1 and 1.5 electron volts. You should lose about 0.4 volts because you can't push these quasi-Fermi levels all the way to the band edges. Now, the quasi-Fermi levels represent the chemical potentials for electrons and holes, and so we can figure out finally that the maximum voltage that can ever be stored inside the semiconductor by steady state excess hole concentrations can be measured from VOC, and that's literally the quasi-Fermi level splitting for electrons and holes under the conditions of light illumination. So we've talked about the limitation on photon flux, and as you get larger and larger in band gap, you get smaller and smaller current, and as you get smaller in band gap, you get more current. But then we see here that a good rule of thumb for VOC would be approximately E gap minus 0.4 volts, and in voltage terms, we have to divide by a Q here. And so you have linear proportionality here. So therefore, the maximum efficiency for photovoltaics can be argued to be a function of band gap, and it looks sort of like an upside-down parabola with some wiggles and details due to these holes in the spectrum. Maxes out at about 31% efficiency, and that occurs somewhere around 1.3 eV, with basically the region between 1.1 to 1.5 EV giving very good performance. And the details of the semiconductors and how good they are in terms of tau tend to matter more these days in defining the efficiency for any given semiconductor, because this thermodynamic limit is very difficult to reach. So this, a more detailed and rigorous derivation of this is called the Shockley-Queisser theory, and it, unfortunately it's beyond the scope of this class. But the main ideas have been captured here, that low band gap gives you more current, high band gap gives you more voltage, and somewhere in between is a maximum point here. Okay, so now let's connect back to the one last point here having to do with the expression here for the currents. I'm going to lump those together and say that my JV curve is given by some J naught, and we're going to approximate that we're operating in sufficiently high forward bias that we can ignore the -1 part here, and that's a good approximation if you look here, because the maximum power point is indeed very close to VOC instead of being close to the origin. So we can approximate the JV curve to very good accuracy as QV, exponential to the QV over neta KBT, where this neta we're going to let be any number greater than 1. So now if we want to find out the relationship between the currents flowing in the solar cell and the open circuit voltage, we have to add one more thing, which is the J light. And depending on how you're defining your currents and voltages as positive or negative, this could be a -1 or a +1. The way I'm drawing it here, it's a -1, but if you flip the curve upside down, which is sometimes done, sometimes you see curves like this to keep all the currents positive, you would flip that sign. So anyway, if we want to look for the open circuit voltage point, we're going to set this total equal to 0, and so we'll have eventually that exponential QV OC over neta KBT is equal to J light over J naught. Invert the whole thing, solve for VOC, and we have the J light is set entirely by the band gap of the material. It's very insensitive to recombination, it turns out. However, this J naught is very sensitive to recombination, because in reverse bias or even zero bias, if you have a recombination center, it's also a generation center inside the depletion width, because the carrier densities are lower than their equilibrium values. Therefore, there will always be thermal generation. So if there are impurities in the semiconductor, this J naught term will go up, and the VOC will be dropped. So that's equivalent to saying in the previous discussion that the minority carrier lifetime will be lowered, and thus the steady state excess carrier concentrations will be smaller, and thus VOC will be lower. So the name of the game in photovoltaics is to reduce this dark current by eliminating all sources of recombination generation and making your diodes as good as possible. Now, it may appear here that making neta bigger than 1 is a good idea, but this effect here greatly outweighs it. This is a linear scaling, whereas this is usually many orders of magnitude change for a tiny bit of recombination. So, in conclusion, to make good solar cells, we want to reduce recombination everywhere in the material and its boundaries, the surface recombination as well as all sources of bulk recombination. And we also want to choose a semiconductor that has a near optimal band gap, although the engineering that goes into making recombination small is really where the winners in terms of materials are determined. So good materials for solar cells these days are silicon, gallium arsenide, and then some of the thin film materials that I work on myself, such as cadmium telluride and copper indium diselenide. All these materials perform very well above 20% at the time of this video recording.